Hello, calculus followers. Welcome to the halfway point of this long chapter, chapter 4. 4.5 is a doozy. It's very, very important, though. It's a lot of the things that we've been building up to, and we're going to talk about the derivatives and how we can use them in order to find out definitely the key parts, but even the other shapes of our entire graph. So we're going to build off of a lot of the stuff we've been talking about in the first few sections, namely the previous one. The very end, we talked about how we can figure out where our graph is increasing or decreasing. That was where the derivative was positive, it increased, and negative decreased, because remember, the derivative is simply the slope of the tangent graphically, but it's more importantly the instantaneous rate of change. And if it is a positive rate of change, then that means something is increasing, whatever those things are that we're comparing. And then similarly, negative, meaning it's going to decrease. In order to figure out where it was positive and negative, remember we also found where the derivative was equal to 0. And because those points were so critical to us, we called them critical values or critical points. We then used those things to figure out where we had a relative max or min, and even the endpoints to figure out if there's an absolute max or min. And that takes us into this section where we are going to utilize all of that information and not exactly sketch or draw this thing out, but pretty darn close, finding important values, critical, dare I say, for us to figure out those high points, those low points, and exactly where they're at, and then trying to use some of the other stuff where it's increasing or decreasing to come up with the basic shape of a graph. So let's get to it. And let's start with going back a couple of sections to 4.3. This was definition number 5. And we said if there is some value c in the domain of our function, we call it a critical number, value, or point if f prime of c equaled 0 or was undefined or did not exist. That is critical for us to be able to find those highs and lows we called local max and mins, or extrema. Again, that was in 4.3. Then there was another important thing in 4.4. This corollary off of a theorem said that, as most of them did, if it's continuous over a closed interval and differentiable within that interval, then if our derivative was greater than 0, that meant over that it was increasing, and if it was less than 0, then it was decreasing within that interval. And if you didn't just get done watching those, then here's that quick review of some key concepts that we are now going to use to introduce and figure out some important concepts, not just on our graph, but also that we could apply in the real world. And the first one is called the first derivative test. So this is a very important one that we are going to use quite frequently. Let's see what it entails. It states that if we have some critical value, again, we're going to call it c, and of course it's continuous and differentiable, except maybe at that value where it does not exist, as we mentioned up above, then 3 things can happen at those critical values. Either our derivative changes from a positive to a negative value at that value c, or it's going to change from a negative to a positive at that value c, or there could even be no change of our signs around that value c. And if it goes from a positive to a negative, then we should know that that would be what is called a relative or local maximum. And if it was changing from a negative to a positive, then we know it is a relative or local minimum. But if it doesn't change, then it does not have a relative max or min at that value C. So we're going to use the fact that we know how to find those critical values, those places where we have that horizontal tangent, or it does not exist, a vertical. But we're going to find those critical values, and then we know that if those are the only places where it's equal to 0, whether it's on the top of a fraction or the bottom, then if those are the only places it's 0, it either has to be greater than or less than to the left or the right of it. And knowing that it either increases if it's positive or decreases if it's negative, then if it shifts from one to the other, then around that we can tell without graphing that it is a local max, or from negative to positive, a local min. And if it doesn't change, then it's not one of those maxes or mins like we talked about in the previous video. All right, hopefully that makes sense. Why do we call it the first derivative test? Because what are we going to do? We will find the first derivative, and then secondly, we will test values on both sides of that 0, that critical point, in order to see whether it's positive or negative on both sides of our 0. So to elaborate on this, to think as a little bit deeper than just x's and y's and on a flat Cartesian coordinate plane, what does that actually find for us? Remember what the first derivative found for us? It was the slope of a tangent. But what did it actually represent? Was the instantaneous rate of change. So looking at what we called higher order derivatives, second, third, which we said applicably was the velocity for the first derivative, acceleration, and even the jerk we talked about. If we looked at the rate of change of our position, then that was velocity. The rate of change of our velocity was acceleration, and if we looked at how that changed, you're looking at how you jerked. We're going to talk about what the second derivative finds for us then, like we talked about here. And we know that when we found that first derivative and set it equal to 0, we called it a what? And what did it represent? Well, we called it a critical value, number or point, and what it found for us was where the possible local max and min were. If we wanted the global or absolute, we had to test our endpoints and see which ones came out higher or lower. If, of course, it was continuous on a closed interval. Well, then thinking about all of that, what the first derivative found for us and what it actually represented, what would the second derivative find for us and represent? Go ahead and pause it right here and think about it if you got a few seconds. You want to stretch and work that mind out and grow it. Think about what that second derivative would both find for us and represent. Were you able to come up with anything? If you think about if this is the instantaneous rate of change or the slopes of our tangents, then if we found the derivative of that, our second derivative, then would it be the instantaneous rate of change of those? Well, this one isn't as obvious or intuitive. So when you take that second derivative and set it equal to 0, we're going to call these things our point of inflection, is what you get when you set the second derivative equal to 0. And any place where it's not 0 is what is going to find your concavity. So instead of our slope of our tangents, it will now find how curved it is and what direction that curvature is facing. So these are the types of things that we're going to get into now. A little bit confusing at first, so bear with me. Let's talk about the definitions. We'll take a look at this, and then, of course, do some examples to help us put it to work and put a finger on it. So this next definition here, concavity, we're calling it again, 4.52. We need a differentiable function if we're going to be finding concavity, which is going to be second derivative, right? We're going to take the first derivative and start there, and we are going to say that if it is increasing over some interval, our derivative that is, then we say that it is concave up. So again, if our first derivative is increasing over some interval, we are going to say it is concave up over that interval. Where you can probably guess, if it is decreasing, then it is concave down. So we're going to talk about this several different ways, and we're going to have options because sometimes it's easier to use one way than another. But again, one more time, in order to figure out if there's concavity, we'll look at the first derivative, and if it's increasing, meaning boom, 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 then we're going to say it's concave up. Where if the first derivative is decreasing, negative, then we're going to say it's concave down. So we'll talk about concavity in several different forms, but first, we're just talking about the first derivative. And if it's differentiable, we take the derivative and we notice that those derivatives over time are increasing. So the slopes of our tangents are getting bigger and bigger and bigger for some interval, and we're going to say that it is concave up. Likewise, decreasing, down. So if you wanted to think about this graphically, right, there is an easier way to kind of think about it, and that is just where would my tangent lines be? Now, we may not always have this option because the graph may not be there, or we may not want to or know the graph. So we're going to need an algebraic way to do it as well, which is one of these. We'll see another one in a second. But if the graph of your function lies above all of its tangent lines, then we are going to say it's concave up. Where if the graph lies down below, our function is below all of the tangents. Think about it like this, right? All of the tangents that we would draw would be here. So our function would be below it. Then we're going to say that this is concave down. And I like to use a little acronym here to kind of remind you, if it's concave up, then it's going to look like a cup. Where if it's concave down, it will look like a frown. Okay, hopefully that'll help you. This is just a visual without the actual graph. We'll get there. Remember when we took the first derivative and set it equal to 0? Those were our critical points that we talked about. And it helped us to figure out on the other sides of those zeros whether our first derivative was increasing or decreasing. Well, then what would happen if we took the second derivative? Or where it's changing from concave up to concave down, there also has to be a point or place where that changes. And we call that a point of inflection. So again, the definition here is if it's continuous and it changes concavity at some value, we're going to call it the point A, comma, f of A, then it is called the inflection point, or where our slopes of our tangents would reflect to the other side in order to continue to have tangent lines instead of secant lines, where it only hits at one place on the outside of our function. And how do you think we find these? Well, remember the critical points was the first derivative. Second derivative is now going to be our way to find the point of inflection. So instead of using the first derivative to figure out concavity, you can also use the second derivative. As long as you can take the derivative twice on whatever interval you're concerned with, if it comes out positive, then we will say it is concave up. And if it comes out negative, concave down. So again, just like before, when we took the first derivative, we set it equal to 0 to find those critical, important points, and anything to the right or left of it, we tested to see whether it was positive, increasing, or negative, decreasing. Well, now we're going to take the second derivative and set it equal to 0 to find the point of inflection, which at that point, to the right or to the left of it, is going to tell us now where it is concave up for positive or concave down for negative, where our curve is shaped, pointing up or pointing down. So what do we mean by all of this mumbo jumbo, lots of words and algebraical expressions? here's a graph of some curve, kind of looks like a sine or cosine wave. What would be true about these points in particular? Well, if we look at every one of those tangents that have been drawn, again, notice that they are on the outside. So where does my function lie? Well, here to here, it's above. My function is above. My tangent lines are below. So if my function is above, it is pointing up. Where here, my tangents, my graph, my function is below. And so you can see it's pointing down. And there's one place in particular where it changes from what is called concave up to concave down. And that, my friends, is what we just defined as an inflection point, or POI, point of inflection. So you can see that this and this are those critical points where our derivative of this thing would be equal to 0. And to the left of it, we would have negative tangents. Here we would have positive tangents. Here we would have negative tangents. But if we took the second derivative, how is it changing? Well, this is tricky. Now we're looking at these as what they are doing as we go from one to the next. And as you can see, it is getting more and more and more negative, which means we would have concave down here. As we move here, more and more and more negative to a point, then it starts to get less and less and less negative. So graphically, these things can help, but wanted to get you an idea of how things are changing, whether it's the first derivatives or the second derivatives. Positively, negatively for second derivatives. These are all the things that we're going to have to now do. And I'll summarize this all at the end. So that takes us to our next theorem called the second derivative test. This one, just like the first derivative test, is going to tell you exactly what you need to do. That's first, take the second derivative, figure out where it's equal to 0 to find your new things we're going to call points of inflections. And once you've found everywhere your second derivative is equal to 0, those points of inflection, where it changes concavity, then you will test around it to figure out where our second derivative is either positive or negative. Not increasing or decreasing anymore. The first derivative, remember, was our critical points when we set it equal to 0. And then when we tested about it to see where it was positive or negative, it was where it was increasing or decreasing, our function was. So you can see right here, that's where it was 0, negative, negative, so decreasing for our first derivative, 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 derivative for these, increasing, still increasing. But then it hit that 0 again for that slope of that tangent, that first derivative. And then decreasing for all of these, negative slopes. When we find the second derivative, though, you can see over here, how is it changing? And by it, now we're talking about the first derivative. How is it changing? Well, it was pretty negative here, getting less and less negative until it got to 0, and then it started increasing. So you can see the change was that it was getting bigger and bigger and bigger and bigger, which is why it's positive. Started off pretty negative, went to 0 and just kept getting bigger. But at a point, it started getting our slope of our tangent less big or smaller until it got to 0 and then started getting more and more negative. So now here, our second derivative, our rate of change of our first derivative was decreasing and therefore negative. Concave up. There's my cup. And concave down. There's my frown. So how can we do that with the second derivative test? First, we will find our critical point or points and making sure that we are continuous over our interval that has that C in it. Then we can simply just test the one and only point that we know in the second derivative, whether it's positive or negative. And sometimes, of course, it can even come out a 0. And we'll talk about what happens when that happens. And if that thing in our second derivative, that critical value, comes out to be a positive. What does that mean? Well, if our second derivative is positive, that means we will actually have a local minimum. Now, I know that seems counterintuitive, but let me explain why. If the second derivative comes out positive, then that's going to give us concavity going up, which means at that critical point, there will be that lowest value. Again, counterintuitive, so you can probably guess what happens when it comes out negative, our second derivative at that critical point. If it comes out negative, then that means it's going to be concave down at that point, which means we will actually have a maximum. So what then happens if we were to get a 0 at that critical point? Well, then that means that the test, unfortunately, fails because we don't know if it's concave up or down. That critical point is actually also going to be a point of inflection, and therefore means that the second derivative test is inconclusive. It failed to tell us whether it was a max or a min at that critical point. So we will have to go back and use the first derivative test in order to do it. Now you may be wondering if we already have to figure out where we got our critical points, where those C's are at, why would we ever take the second derivative to do this? It really just depends on the function. If the function is really easy to take the second derivative of, then we might as well just quickly do the second derivative once we've already found our critical points, and then plug that in to see whether it's positive, therefore a minimum because of concavity, concave up, low point, or if it's negative, concave down, so we'd have a maximum at that. So if your function is pretty easy to take this second derivative of, then you can use this second derivative test. If it's not, then you're always able to use that first derivative test without fail. You're just going to have to test some points to both sides of your critical value in your first derivative of that 0 to see whether it's increasing and then decreasing for a max or decreasing to increasing for a min. Let's summarize all that. That's a lot of information. Check this out. As I just mentioned, the first derivative test is what I lean to just because it always works. But as mentioned also, the second derivative test is sometimes superior because we've used and seen some of these derivatives are really quick and easy to take the derivative of. So then we don't have to test multiple points. We can just test one point, our critical value. And also recall that although these are very, very similar, hence the names, first derivative test and second derivative test, you got to know the difference between the two and what you are using and what it's finding for you. Just because they're almost the same doesn't mean it finds the exact same things for us. All right, so let's take a look at what all of this would look like for both the first derivative and what it finds for us, how we use it, and then the second derivative test in nice, complete charts. Okay, this is really good for your notes. Already filled it in, just want to highlight some things. Remember, first derivative is given by that symbol, and once we've taken it, we next want to find our critical points by setting that first derivative equal to 0. So whether you call them critical numbers or values, that's just the x. If it's a critical point, then technically you'd have to plug in your x to find your y. And oh, by the way, remember, we're doing all of this, whether it's the first derivative stuff or the second derivative, it's all for the original function. So if you're ever going to give me my critical point or your point of inflection, remember, wherever you find those x's, you're going to be plugging them back into your original function, f of x. Once we have found those critical points and set it equal to 0, we will then create what we call a sign chart to only focus on whether it's positive or negative, what the sign of it is, to tell whether it is increasing or decreasing, if it's positive or negative. And remember, we can then also use the fact that we know that it goes from one to the other to figure out if it's a relative max or a relative min at that value C, however many there are. Now, if you hit the reset button and do that for the second derivative, you're basically going to be doing the same steps, these 3 steps. But for the second derivative, it finds different things for us. So again, we will still set it equal to 0, but now instead of the critical points or values, now it will find the possible points of inflection. Possible because we can have some issues, as we mentioned. Once we find that, or those, however many there are, just like we did with the first derivative, we will now take the second derivative, those points of inflection, and create a sign chart around them. But instead of it telling us where it's increasing or decreasing, and by it, again, doing everything for the original function, but using the first derivative, the rates of change, whether it's the first or second derivative, just find something different, where our function is increasing for the first derivative or decreasing, where the second derivative is going to find the concavity, the shape of our graph. And if it's positive, remember, it will be concave up, cup. And if it's negative, then it will be concave down, frown. And at those points of inflection is where it changes from one to the other. If you can take that second derivative and plug in your value, your critical point, and it comes out negative, then that means we know that it is concave down, and at that critical point, which we got the first derivative is equal to 0, we know it would be a relative max there. Where if we took the second derivative at our critical point where the first derivative was equal to 0, and the second derivative came out positive, then that means we know it's concave up at that point, and therefore it would be a relative minimum. And every once in a while you'll get that special case where it's unfortunately inconclusive because it's both a critical point and a point of inflection at that value, and therefore it doesn't tell us if it's a local max or min at all. And we got to go back and use the first derivative test. A lot going on there. Hopefully this summarized all of the first derivative, second derivative stuff. And again, notice that all we did was basically the same thing, but what it finds, even if we're trying to find these, how we do it is much different. First derivative, critical points, tells us where it's increasing or decreasing, whether it's positive or negative, about the zeros. Second derivative equal to 0, points of inflection. Now, if it's not 0, it's positive or negative, it tells us the concavity, the shape of that curve. That's all I got for you for this. Very, very important concepts. Make sure that you work hard to understand not only what and how you're doing it, but what it is finding for you. Just as a reminder, it's going to take time to get the hang of this. And as the saying goes, practice makes not perfect. Because if you practice it incorrectly, that's what you will perfect. Practice makes permanent. So make sure that you practice correctly so that you permanently know what you're doing, what it finds for you, and how to get it done. So be careful. Make sure that you continue to work with each other, our TAs, and myself. And as one precautionary thing before I let you go, common mistake that I've seen with these is people not putting in things to the proper places. Meaning, remember everything we are doing, the first derivative, second derivative, all of that information is always for our original function and how to graph it. All those key points, critical points, points of inflection, concavity, where it's increasing or decreasing. And remember what each derivative finds for you. The critical points, increasing, decreasing, points of inflection, and where it's concave up or down. Keep working at it, master it, and then we will move on. But work hard. The process is very similar, which can be confusing, but it's also nice because you know what to do, whether it's the first or second derivative, set it equal to 0, know what that finds for you, test on both sides of it, know what that finds for you, and then know what you can find based off of that information. Take care, everyone. Hope to see you in the next video.